Let's continue and conclude our discussion of the resonance patterns that you want to have on the radar when you're looking at structures and trying to decide if you can draw resonance. So we talked about the allele cation and the allele anion patterns, and now let's look at the allele radical. So the radical, before I start drawing, a radical is a chemical species with an unpaired electron. So what the allele radical pattern is going to show us is how to handle electrons moving individually instead of in pairs, which is what we've been doing. So let's draw an allele radical. And an allele radical is going to have an unpaired electron, a single electron, on the allylic carbon. Okay, so the way to draw this is to use the fishhook arrow. So one barb instead of two. So this is what we're going to do. We're going to take two electrons from the double bond, but we're going to split them up. We're going to put one on this carbon, and we're going to team the other one up in a new double bond with this electron on the right-hand carbon. So the result of those arrows looks like this. Now let's repeat that using the skeletal format. So split apart two electrons from the double bond, and then bring one of them into a new double bond with the unpaired electron that's on the right side of the original structure. Let's look at another example of this in the context of a more complicated picture. So let's look at this guy. Okay, again, when you're looking for these patterns, look for things like double bonds, triple bonds, and charges, as well as unpaired electrons and lone pairs of electrons. So non-bonding electrons, charged things, and multiple bonds. Those are the features that you're looking for. So we have that right here. We have an unpaired electron at the allylic position. And so we'll do exactly the same thing with it that we did in the simpler example up above. Okay, you'll be pleased to know, well, I'm not sure I can back that up. You may or may not be pleased to know that a benzylic system is really just an extension of an allyl system, the way that we think about it in terms of resonance. So let's take a look. Okay, so the first thing, here's benzene. And then I'm going to draw a few other examples of benzenes that have things attached, carbon atoms specifically, to remind you that a carbon directly attached to a benzene ring, that is the carbons that I've highlighted in these structures, is called a benzylic carbon. Any hydrogens that would be attached there would be called benzylic hydrogens. Okay, so the first thing that we can do with benzene is the following. Let's just look at benzene by itself, and then we'll look at these benzylic ideas. Okay, so the conjugated double bonds in benzene, we can shift around the ring. So that's one resonance structure that we can draw. And we would draw it as follows. So start an arrow. Actually, you know what? I'm going to draw that bigger because that is really small and hard to see. Okay, that's better. All right, so what you're going to do, and it doesn't matter which direction you do this in, if it's clockwise or counterclockwise, that doesn't matter. But you're going to start an arrow at each of the double bonds and point to the single bond next to it, and just shift them all around the ring in that fashion. And as you might guess at this point, and you'd be right, these are equivalent contributors. And what they're doing is showing the delocalization of electron density around the ring. So sometimes to draw the resonance hybrid of benzene, people just draw a circle in a hexagon. So this is the resonance hybrid. So benzene and other aromatic compounds have their own special set of resonance moves, or their own special resonance moves, which is what I just showed you. So you can move electrons around a ring in this fashion. Now for benzylic systems. So now you have something attached to the ring, a carbon atom attached to the ring. These follow exactly the same pattern as the allylic systems. So let's go through and start drawing. So we'll start with something called a benzyl cation, or you could call it a benzylic cation. Either way is fine. So here's an example of a benzyl cation. Now, there doesn't have to be just one carbon. So for example, the carbon that has the positive charge, that could have some other carbons attached to it, a chain that extends off to the right or what have you. But just to keep it simple, we'll just leave it at one carbon. Just so you know that this is a smaller pattern that can appear in molecules that have more atoms. So you recognize the double bond next to the positive charge, which is nothing more and nothing less than an allyl cation. So start an arrow at the double bond and point to the bond next door to it. So move the electrons in the direction of the positive charge. That leaves us with this. But we're not done, because now we have another allyl cation pattern. And so we're just going to repeat the move. And that gets us to this structure. And we have another allyl cation. So we just keep repeating this pattern. And finally, we have one more structure that we can generate. And that would be this one. So that's for the cation. There's something called a benzyl anion. So let's take a look. The benzyl anion, as the name implies, has a negative charge and a lone pair at the benzylic carbon. So we recognize the allyl anion pattern. Lone pair next to double bond is what we're looking at here. And we know how to treat that from our study of the allyl anion. Which is to say, start an arrow at the lone pair, move it into a bond, and then break a pair out of the double bond onto the far atom. Once we generate that structure, we end up with another allyl anion. So we just repeat the process. Notice the artistic license, the placement of the arrows, whether I have them inside the ring or outside the ring, doesn't matter as long as where they start and point is really clear and really precise. We have another allyl anion, so we're going to continue. And you can imagine where this is going. So we end up with a final allyl anion that we treat the same way we always treat allyl anion types of patterns, or lone pair next to multiple bond. Whether there's a charge or not, of course in this case there is, but as we saw with the carboxylic acids and derivatives, the lone pair next to double bond pattern doesn't necessarily have to involve a charge. Okay, let's do one more example here, and this is the benzyl radical. Okay, so we notice the allyl radical pattern, and that means that we're going to treat this exactly the same way we treated that. So 3 fishhook arrows. Which generates another allyl radical. And so we just keep applying the pattern. And there's another one. Now, as you can tell, we're going pretty much to the same place. So I think we've drawn enough resonance structures for now. You can finish out the other ones on your own time. Well, actually, it's all your own time, but so it's the same. You just look for the same pattern and keep applying it wherever you see it. Okay, let's look at some more patterns. Let's do an exercise involving an ion this time. So we're going to do the acetate ion. Now you might remember the acetate ion from Gen Chem 2 when you studied acids and bases. So let's just brush the dust off of a little bit of the acid-base terminology. We're going to get to that in the third packet, but there's no time like the present to start. Here's acetic acid. And we know that acetic acid is a carboxylic acid. If we reacted acetic acid with a Bronsted base, the Bronsted base is going to accept the proton that I just highlighted. And by accepting it, I mean it's going to pull it off and bond with it. So it's going to remove it from the acid. When that happens, you get the acetate ion, which looks like this. So this is the acetate ion, which is an example of a carboxylate. So this is something called a carboxylate or a carboxylate ion, which is the conjugate base of a carboxylic acid. Okay, so that is the acetate ion, and that's also a little mini reminder of what you were doing in Gen Chem 2 when you're doing acids and bases. So the idea of conjugate acid-base pairs is going to slowly come into play here. All right, so let's draw the acetate ion. Like so. So just reproducing the structure from up above. Okay, let's call that structure A. Okay, Now, we know that when we have a multiple bond, a double or a triple bond, between two atoms that don't have the same electronegativity, that we can move electrons out of the bond and put them on to the more electronegative element. So let's just do that first. That's not to say it's the best move. That's always going to just generate a minor contributor, but sometimes it's a good starting point. Okay, so remember that when we do that, that puts a negative, in this case, it puts a negative on the oxygen and a positive on the carbon. So now what we have is this pattern that I've just highlighted. You have an atom with at least one lone pair, and it's bonded to an atom with a positive charge. So we saw this pattern a little bit earlier, and what you would do is just move in a pair of electrons into a double bond. So move them toward the positive charge, or toward the atom with the positive charge. Okay. So you might be aware of the fact that this is a lot like what we did with the ester, and by extension with the amide. So what I would like you to do now is pause the video and assess which of these is the important, or the major contributor, the most important contributor, and which is the most minor contributor. So before we do that, let's label these as B and C. So now we have all the structures labeled. So pause the video and make an assessment using those guidelines that we talked about earlier. Once you've done that, hopefully what you're finding and what you're observing is the following. In structure A, all of the atoms have octets. Also in structure A, formal charge is minimized. Now you might think, well, wait, we have a negative charge. Yeah, but it's still minimized. The charge in the structure is still minimized. It's an ion, so it's going to have an overall charge. So you're going to have some element in there, at least one element that has charge on it. So the fact that we don't have charges anywhere else suggests that we've minimized the charge. In structure B, we have some problems. First of all, the carbon lacks an octet. Formal charge is not minimized. And we've got separation of charge. And finally, in structure C, again, all the atoms have an octet. And we have minimized formal charge. Now, if you look at structure A and structure C, as it turns out, A and C are equivalent contributors. And they're both major for the reasons listed above. Now, this idea of equivalent contributors, again, you might think, well, they look like the same thing. If I just turned one of them over, flipped one of them over, it's going to be the identical thing. Now, that's true. They have identical energies because of their internal features, but they're not the same structure. In structure A, the negative charge is borne by this oxygen. In structure C, it's borne by the other oxygen. So the negative charge is being shared between the two oxygens. In fact, you could draw the hybrid. I'll just do this over here on the side. You could draw the hybrid something like this to show that that negative charge is delocalized. So although they are equivalent, they're not exactly the same structure. And then B, of course, we would consider the minor contributor. Let's do this for another compound. So this one is also an ion. It's just a positive ion. So this is a cation. So CH2NH2. Like I said previously, oftentimes when they give you a formula, they give you the atoms in the order in which they're bonded. So let's start by drawing this structure. Okay, when we count up all the valence electrons, this is what we come up with. Okay, so here we have an atom with a lone pair directly bonded to an atom with a positive charge. So we know what to do in that case. We are going to pull a pair of electrons off of the nitrogen, put them into a double bond. Okay, so here's the resulting structure. Now take a minute and look at that structure and see if you can tell what's missing. If you said that there's a formal charge missing, you are correct. There should be a formal charge of +1 on the nitrogen. Now this makes sense because charge, remember, has to be conserved. Each of the contributors to the hybrid has to have the same net charge. If we go back up to the acetate ion, we can see that that's the case. Each of the structures that we drew has a net charge of -1. So that's up here, -1. I'm drawing a little bracket, so that it looks like a 7. Maybe I should just leave that out. That could be confusing. Oftentimes when people are putting a charge on a structure, they'll do something like that. So let me just put a bracket around the whole structure. This is -1, this is -1, and this is -1. So the charge is conserved across all the structures. So that's the case down below as well. Okay, so pause the video and figure out which of these is the major contributor and which is the minor contributor. Hopefully now that you're back, you said that it's the structure on the right that's the major contributor. You'd be correct if you said that, because all the atoms have octets. And again, a highly electronegative element such as nitrogen or oxygen with a positive formal charge is okay as long as it has an octet. Now, let's focus in on these two structures. In the structure on the left, there's a single carbon-nitrogen bond. And in the structure on the right, there's a double carbon-nitrogen bond. So which of those is longer and which one is shorter? Okay, so if you said that the single bond was longer and the double bond was shorter, you would be 100% correct. And so the question that I have for you now is, what is the actual bond length? Is the CN bond length in this structure, is the CN bond length, or in this ion, I should say, is the CN bond length that of a single bond or a double bond, or is it neither of those things? So this is another point or another place where drawing resonance structures gives us a little more information than we would have had we only looked at the major contributor. So one of the contributors here shows a single bond, and the other contributor shows a double bond between the same two atoms. What that suggests to us is that the actual bond length is somewhere in between that of a single bond and that of a double bond. So the answer here is that it's neither a single bond or a double bond. The bond length is between that of CN single and CN double. And it's probably a little closer to the CN double bond because that's the major contributor. So that's the better depiction of the molecule. Let's look at one more idea, and then we're going to go through a summary of all the patterns and look at some more examples, and then we'll be finished with the packet. So let's look at this situation right here. So let's say that you want to do something with that lone pair, so you decide to do this. Is that an allowable move? Okay, well, let's redraw the structure with a little more detail and see if it is or not. So the carbon right here, the highlighted carbon in the original structure, it's the same as the one I've highlighted in the structure below it, has two bonds that are explicitly drawn. Thus it has two hydrogens, which we did not explicitly show in the original structure. That's an sp3 hybrid carbon. So a carbon with 4 single bonds is an sp3 hybrid. As such, if we tried to move electrons toward it, we'd have a structure like this, which is horrible. So now this carbon is involved in what we would call an egregious violation of the octet rule. It's not just a violation, it's egregious. It's an egregious violation of the octet rule. You've exceeded the octet. You can never do that with a period 2 element. So never exceed octet on period 2 elements. So the rule of thumb here is what we were trying to do was move electrons toward an sp3 atom. So you want to avoid that. Avoid moving electrons toward an sp3 hybridized atom. So that's a common mistake. Another common mistake involves drawing structures that have violations of the octet rule. So be careful, assess your structures after you draw them to make sure that those things are not happening. Okay, let's wrap it up by looking at all the patterns that we've looked at and looking at some new examples of each of them. So if you have a double or a triple bond between two atoms that have different electronegativities, such as the case here, that is really crammed in there, but it's too late. You can always pull electrons out of the double bond and put them onto the more electronegative element. So the electrons that came out of the double bond are now in the form of a lone pair on the nitrogen, and the carbon ends up with a positive charge. So I'm going to redraw to make it a little clearer. It's a little better. Okay, a double or a triple bond next to an atom with a positive charge. That's the allyl cation pattern. It involves that one curved arrow to shift electrons over toward that positive charge. Now the positive charge has to be right next door. It can't be too far away. So here, no resonance is possible. A double or a triple bond next to an atom with a lone pair. So we saw this compound when we were talking about functional groups. This is phenol. Phenol exhibits this pattern. The oxygen has a lone pair, which we can push into a double bond, and then break two electrons out of the double bond next door and put them onto the carbon. That leaves us with a positive charge on the oxygen and a negative charge on the carbon. Let's do another one of these. This is a compound called furan. Again, not a name to memorize. But we have the same situation. The oxygen has two lone pairs. You can move one of them in either direction and push a pair out of a double bond. So by either direction, I mean you could have also gone this way. That gives you this structure, which has separation of charge in it, so it's a minor contributor, but it's still an allowable resonance move. If you have a double or a triple bond next to an unpaired electron, a radical, so here's the allyl radical pattern. And remember, we need 3 fishhook arrows to show what's going on here. So at this point, all we're doing is memorizing the patterns of the allowable moves so that we can practice them and apply them until we can apply them without thinking about them. Later on, we'll learn why these are the allowable moves, what's actually going on that we can only draw these arrows. And remember that all of these allyl patterns extrapolate to the benzylic systems as well. Now, we looked at this a little bit. If you have conjugated double or triple bonds, we looked at this in the context of benzene, but let's look at it in a couple of different pictures as well. So let's say you have this. These are conjugated double bonds because they're separated from one another by just one single bond. So you could do something like this. So let's fine-tune this arrow so that it's a little bit clearer so that we have exactly what we want. We're going to move those into the double bond. That's going to leave the carbon on the left with a positive charge. We took electrons out of the double bond on the right part of the structure and put them onto the carbon on the right, which gives it a negative charge. So we have a charge-separated minor contributor there. Another example of this that we saw was when we were talking about how you assess the contributors. This was one of the examples that we used there. And there we did this. Like so. And then finally, if you have a lone pair on an atom next to an atom with a positive charge, like you have here. Here's your pattern. You just take one of the lone pairs off the oxygen, move it into a double bond. That's going to give you a major contributor because you've satisfied everyone's octets. That means it's okay to have that positive charge on that oxygen. And that brings us to the end of the packet.